In the previous few lectures, we have seen the basic fundamentals of the beta decay process. Now it is your time when you will discuss the proper theory of this beta decay process. In fact, in 1934, a famous Italian scientist Enrico Fermi formulated a successful theory of this beta decay process. And this theory is actually based on the famous neutrino hypothesis proposed by Pauli. And you have seen the basic fundamentals of this neutrino hypothesis in the previous lecture too. In fact, this Fermi theory of beta decay is actually a vast concept. So I have divided this lecture in two parts. So you can say that this is actually the first part of the Fermi theory of beta decay. And you will see only one calculation regarding this Fermi theory of beta decay, and that calculation will be of the probability of emission of beta particle from the nucleus. And in the second part of the lecture, we will see the other important facts of this theory. In fact, this Fermi theory of beta decay is based upon some important assumptions. So first of all, we will see what are the assumptions on which this Fermi theory of beta decay is based on. And after that, we will develop or we will actually discuss the proper theory of beta decay proposed by Fermi. So let us start to know what are the important assumptions on which this Fermi theory of beta decay was framed. Some of the assumptions you know already. You know, in case of the first assumption, you can say that during this beta decay process, you have seen earlier that the light particles, electron and neutrino, are created by the transformation of neutron into a proton inside the nucleus. And at the same time, inside the nucleus, a proton is also transformed into a positron and an antineutrino. So, in the first assumption, we consider that inside the nucleus, a neutron is transformed into a proton, and at the same time, two light particles are created. The first one is electron, which I have denoted here by E minus, and another particle is antineutrino, nu bar. Okay, and proton is also converted into neutron, and two light particles, that is positron, this E plus is positron, which is antiparticle of electron, and neutrino is created and emitted too. The second assumption is that the energy conservation principle holds in this process. So you can say that energy remains conserved during this decay process. Okay. The third assumption says that the rest mass of neutrino is very small compared to the mass of the electron, and so we can take without any loss of generality that the rest mass of neutrino is 0. So in our calculation, we will take the rest mass mass of neutrino equal to 0. Okay, this is the third assumption. Now, the fourth assumption says that this beta decay process is just analogous to the emission of electromagnetic radiation by an atom. In fact, you know, when electromagnetic radiation is emitted, then electromagnetic field acts, or electromagnetic field is present. See, in the similar manner, you can say that during the beta decay process, instead of the electromagnetic field, there is actually electron neutrino field. Okay, And you know, when a charge is in accelerated motion, then electromagnetic radiation is emitted, and electromagnetic radiation emission means the quanta of electromagnetic radiation is photon. So you can also say that charge is the source of photon. And in the similar manner, in case of beta decay process, actually the light particles like electron and antineutrino, positron and neutrino, these are emitted. So you can say that our nucleons, that is neutron and protons, are the source of light particles like electron, positron, neutrino and antineutrino. In the similar, just equivalent to electric charge is the source of photon. So here you can compare that charge is equivalent to nucleon and photons are equivalent to electron, positron, neutrino and antineutrino. Okay. Now you know that the nuclear force, that is the nucleon-nucleon interaction, you can say, is a very strong interaction. But on the other hand, this electron-neutrino field is weak in comparison to the short-range interaction which exists between the nucleons, that is the nuclear force. So you can say that this beta decay process is due to the weak interaction. It is a weak interaction process. Okay. Now, for the calculation of emission probability or transition probability, here we apply a quantum mechanical theory of time-dependent perturbation theory. Because you know, time-dependent perturbation theory is applied when actually the perturbation is very weak, very small. And as you have seen in the previous assumption, that in case of beta decay, the electron-neutrino field is very weak, and so that you can say that electron-neutrino interaction is very weak, and this is just a weak process. And so in this condition, time-dependent perturbation theory may be applied. And you will see in just now in the calculation of probability of transition that we will apply the time-dependent perturbation theory. So I have mentioned here that time-dependent perturbation theory is a very good approximation because of the smallness of coupling constants or exceptionally weak nature of the interaction. Since this beta decay process is just a weak interaction, so in this case the time-dependent perturbation theory may be applied. And we will actually apply this time-dependent perturbation theory in our calculation. You will see just now. Now, one thing is very remarkable here, and that is just an assumption that inside the nucleus, the nucleons move with a velocity which is of the order of 1/10 times of speed of light. That is, the velocity of nucleon is almost of the order of c/10. And since its velocity is 1/10 of the velocity of light in free space, or velocity of electromagnetic radiation in free space, so we can make the calculation with non-relativistic wave function. And what is the cause that you can make the calculation with non-relativistic wave function? Since the nucleon's velocity is 1/10 times of the velocity of speed of light. But remember, when you will calculate the total energy of the emitted electron, or that is beta particle, then you must follow the relativistic expression, because this velocity is not very small to speed of light. So in first approximation, in our calculation, we will also neglect the spin of the beta particle, and at the same time we will use the non-relativistic wave function instead of the relativistic wave function. Okay. So these were the important assumptions on which Fermi framed his theory of beta decay. Now, as I have told you earlier that I will actually complete this lecture in two parts on the Fermi theory of beta decay, and in this first part of the lecture I am just going to calculate the probability of beta decay process. Probability of beta. This is actually the basic problem. What is the probability of beta decay process? Is it 0? If the probability comes out to be 0, it means beta decay does not take place. But if the probability of beta decay process is non-zero, that is positive, then you can say that this process will take place. And we will see finally that the probability of beta decay process is not 0, it will be positive. So this is actually the basic theory of beta decay process. Okay, and in this first lecture I am just going to start to calculate the probability of beta decay process. Okay, now see, as in case of beta decay, you have seen that electron and neutrino are created, and as the electron and neutrino are created inside the nucleus, at the same moment they get emitted. It means there is no time lag between the creation of electron and neutrino and its ejection from the nucleus. There is no time lag. It means this is just an instantaneous phenomenon. So we simply say that inside the nucleus electron and neutrino are created and at the same time they get emitted. Okay. And if you want to represent the state of the emitted electron, that is the beta particle and the neutrino, by a wave function, let us denote those wave function by the symbol psi beta and psi nu. It means this psi beta is the wave function which actually determines the state of the emitted electron or beta particle, and this psi nu, it is the wave function which will determine the state of the neutrino emitted from the nucleus. And let us consider that when the electron and neutrino are created and emitted from the nucleus, then their momenta are p beta and p nu. Let us consider. In fact, this p beta is the momentum of, or you can say linear momentum of the beta particle, that is electron, and this p nu is the momentum of the neutrino. Let us consider. In fact, this state function, that is psi beta and psi nu, may be taken just as a plane wave. So treating the wave function as a plane wave, you may write psi beta equal to n beta times e to the power I k beta dot r. Here actually k beta is the wave vector for the beta particle and r is the space coordinate. And this n beta is what? This is actually the normalization factor. N beta is normalization factor. Now you know that the momentum P is equal to h bar times k. You know it. And so what will be this wave vector k? This is simply p over h bar. So instead of this k beta, you may write p beta over h bar. So the same expression can be written as psi beta equal to n beta times e raised to the power I over h bar p beta dot r. And similarly, the state function or the wave function of neutrino psi nu is given as n nu e to the power I k nu dot r. And here again n nu is the normalization factor, k nu is the wave vector for neutrino, and as you have assumed that the momentum of neutrino is p nu, so you can write this expression like this. This is n nu e to the power I over h bar p nu dot r. Okay. So these are the wave functions for the emitted electron and the beta electron and the neutrino. Okay. Now, when you talk about the probability of emission that take place here, that is the probability of emission of electron and the probability of emission of the neutrino, on which factors this probability of emission of these two light particles depend on, now we will see it. In fact, basically there are three factors on which the probability of emission of beta particle and the neutrino depends on. The first one, you can say that the first one is actually the expectation value of the electron and neutrino to be inside the nucleus. It means what is the probability density, or you can say what is the probability of finding of neutrino and the beta particle inside the nucleus. On that factor, the probability of emission of electron and the neutrino depends on. And you know from the Born's interpretation of wave function that the modulus of that the square of the mode of wave function represents actually the probability density. So the probability of emission, you can say, depends on the factor psi beta 0 mod square times psi nu 0 mod square. In fact, here psi beta 0, this 0 refers the r equal to 0. And r equal to 0, it means you are considering that your beta particle and your neutrino are lying inside the nucleus, because 0 refers to the location of the nucleus. We consider that nucleus is just at the origin for and the space coordinate of nucleus is just equal to 0. So when you say psi beta 0 mod square, that is actually the probability density for the finding of the beta particle inside the nucleus, and psi nu 0 mod square, that is the probability density for finding of the neutrino inside the nucleus. So this is the first factor on which the probability of emission of these two light particles will depend on. Okay. Now, the second factor on which the probability of emission of these two light particles depends is actually the square modulus of a matrix element, which I have denoted by the symbol M, and this matrix element is actually taken between the initial and final states of the nucleus. Okay. And in the simplest form, this matrix element may be defined like this: M equal to integral psi p star psi n d tau. In fact, you can see if you are talking about the emission of beta minus, that is electron, then you have seen that neutron is converted into proton, and this E minus is ejected. That is beta minus is ejected here, and at the same time antineutrino is also emitted. So you can see this n state, that is neutron state, is the initial state of our nucleon. Okay, and this proton state is its final state. So here inside this integral, this wave function psi n, this represents actually the initial state of the nucleon, and when you say initial state of nucleon, you can see this is actually the neutron state. Okay, and this psi p is the final state of the nucleon, and you can see this process that final state means the proton state, because initially the nucleon was neutron and it has been converted into proton. So the final state is simply the proton state. Okay, and psi p star means this is actually complex conjugate of psi p. So the matrix element M on which the probability of emission of these two light particles will depend is defined like this: M equal to integral of psi p star times psi n d tau. Okay, I hope you have understand these two factors on which the probability of emission of beta particle or electron depends on. Now, the third factor on which the probability of emission depends is actually a constant factor denoted by the symbol g square. In fact, this is called coupling constant, or in fact the strength of the value of this g square actually determines the probability of emission of beta particle, because you know this coupling constant will be very small, because the beta decay process is just a weak process and a very weak interaction takes place in this condition. So actually the value of this coupling constant g square is g is very small, and actually it is found that this coupling constant g has a value 9 into 10 to the power minus 5 mega electron volt FMS cube. FM means femtometer, and you know 1 FM means 10 to the power minus 15 meter. So what are the factors on which the probability of emission of beta particle depends on? You have seen there are three factors. First one was actually the probability of finding of beta particle and the neutrino inside the nucleus, which we have measured by the probability density by this factor. The second one was actually the matrix element defined between the initial and final states of the nucleus, and that is denoted by this symbol M. And the third factor on which the probability of emission depends is a constant factor g square, and this g square actually represents the strength of the coupling giving rise to emission. And as I have told you, the value of this coupling constant g is equal to 9 into 10 to the power minus 5 mega electron volt FM cube. Now we will apply the time dependent perturbation theory, and using the standard result which you study in time dependent perturbation theory in your course on quantum mechanics, you can find what will be the probability rate. It means what will be the probability of emission of beta particle per unit time. In fact, this result you have to remember, because this result is studied in the theory of time dependent perturbation theory in course of quantum mechanics. So as you have studied time dependent perturbation theory, and so from where you can say that according to time dependent perturbation theory, the probability of emission per unit time, you can also say this is rate of probability of emission. Okay, and that probability of emission per unit time we have denoted by this symbol, this P of P nu P beta dp. In fact, this probability of emission per unit time, that is capital P, depends on the momenta of the neutrino and beta particle. So I have mentioned it inside this bracket. So what is this capital P? This is actually the rate of probability of emission of beta particle. Okay, and this will be equal to what? You have to remember this expression because I have mentioned this result directly from the concept of time dependent perturbation theory. So this rate of probability of emission is given as 2 pi over h bar times psi mod of psi beta 0 times mod of psi nu 0 times mod of m times mod of g whole square and times dne by de. dne by de. What is this dne by de? You can see this dne by de is the number of quantum states of the final system per unit energy interval. It means final system means here the proton, and what is the number of quantum states of that proton for unit energy interval. If it means if for the energy interval dE the number of quantum states of the final system is dn, then for the unit energy the number of quantum states of the final system will be dn by de. So this dn by de represents the number of quantum states of the final system per unit energy interval. Okay. Now, as you have seen that while we have defined the wave function determining the state of the beta particle and the neutrino, we have used a normalization factor. So definitely you have to find the proper value of this normalization factor. And for calculating the proper value of normalization factor, let us consider or you can imagine a very large box, very big box, or very big space you can consider. And we imagine that in that very big box our system is lying. Okay, that our system is enclosed in a big sized box and the volume of this box is V. Then you know, if we take the total probability of finding of a system or particle in entire space, in whole space or all space, then this probability is equal to 1. This is actually called the normalization condition. Definitely you have studied it in your quantum mechanics course. So here V actually tends to infinity because we consider that our box is very big. So V theoretically tends to infinity. It means you are integrating this psi star psi with respect to volume for entire space, for whole space. Okay. So integral over V psi star psi d tau. D tau is the elementary volume, that will be equal to 1. This is simply the normalization condition. Now you have seen what is psi and what will be the psi star. Let us define it. You can write. In general, I am not writing here psi beta and psi and nu separately, but in general we write psi. And you have seen that psi is equal to n times e to the power I k dot r. I have not written the subscript beta or nu here. So at the place of psi I have written n into e to the power I k dot r. And what will be its complex conjugate? Complex conjugate psi star will be n star times e to the power minus I k dot r. Okay. So you can see n star times n. This is a constant factor. So I have taken it outside of the integral. And e to the power minus I k dot r times e to the power plus I k dot r. This product will be 1. So only d tau remains here. Now you are integrating this d tau for the volume V. So integral of d tau will be equal to tau, and when you will put the limit, this will be simply equal to V. And so mod of n square has been written at the place of n star times n, and that will be equal to 1 over V. And so n is equal to 1 over a square root of V. So normalization factor, you can see this is simply equal to 1 over root over V. Now once you have calculated the value of normalization factor, now you can define the wave functions for the beta particle and the neutrino, which we have defined in the first equation. You have seen that psi beta is equal to n beta. Here actually when you write n means both n beta and n nu, both are same, and that is equal to 1 over square root of V. So psi beta will be now equal to 1 over root V times e to the power I over h bar times p beta dot r. And similarly psi nu will be 1 over root V times e raised to the power I over h bar p nu dot r. Okay. Now if you substitute r equal to 0 in this equation, and r equal to 0 refers that our beta particle and the neutrino are inside the nucleus, because r equal to 0, that is space coordinate equal to 0, is for nucleus. Nucleus has been assumed at the origin. Okay. So when the nucleus is at r equal to 0, then what will be psi beta and psi nu? You can see when you will take r equal to 0, this exponential factor in both equations will be equal to 1, because that will be e to the power 0, and e to the power 0 will be 1. Okay. And so both psi beta and psi nu will be same, and that will be equal to 1 over root V. Okay. So the rate of emission, or the probability of the emission of beta particle and the neutrino, depends on what on the first factor, this much. This is the first factor, and you have already calculated what is the value of psi beta 0 and psi nu 0. You have already calculated. So the first factor on which the probability of emission depends, we have calculated, and these are the values. Okay. Now the number of states of beta particle in volume V having momentum between p beta and p beta plus d p beta will be equal to what? We want to find it. Here you have to use an idea of the momentum space. You have definitely studied in your course on particularly statistical physics that in a volume h cube, where h is Planck's constant, the number of quantum states is 1. H cube volume of phase space corresponds to number of quantum states equal to 1. This is actually number of quantum state. It means in h cube volume there is 1 quantum state. Okay. So in unit volume, how many quantum states will be? This will be 1 over h cube. Okay. And when you say that the momentum of our particle lies between P and P plus dP. I am not talking about P beta and P nu here. I am just taking momentum P. Then actually you can imagine a space in the momentum space lying between two spheres having radius P and P plus dP. P plus dP. And the volume in this volume lying between these two spheres will be what? This volume will be differential of 4 by 3 pi p cube. 4 by 3 pi p cube. And what will be this? This will be 4 by 3 pi. And differential of p cube will be what? This will be, I am writing it here. This will be 4 by 3 pi and differential of p cube. This will be 3 p square dp. Okay. Now this 3 and 3 will cancel out. So the volume in this momentum space will be 4 pi p square dp. 4 pi p square dp. Okay. And at the same time, you have considered that there is a box whose volume is V. So volume in phase space will be what? I am writing it here. Actually, volume in phase space is just a product of volume in configuration space or geometrical space, which is V, into volume in momentum space. And volume in momentum space is what? This is 4 pi p square dp. So you can say that for the particle having momentum lying between p and p plus dp, what is the volume available in phase space? That volume, if you denote by the symbol gamma, this gamma is equal to V into 4 pi p square dp. Have you understand or not? Volume in phase space is equal to volume in configuration space, which is V, into volume in momentum space. So the volume in phase space for the momentum between p and p plus dp, that will be 4 pi v p square dp. Okay. Now see here, I have told you that the volume h cube in phase space corresponds to one quantum state. So a unit volume will correspond to 1 over h cube, and therefore a volume 4 pi v p square dp will correspond to how many quantum states? That will be equal to this much divided by h cube. Have you understand or not? So I have written here directly that the number of quantum states of the electron or the beta particle having momentum between p beta and p beta plus dp beta, if we denote this number of quantum states by the symbol d and beta, that will be equal to 4 pi v by h cube into p beta square times dp beta. Okay. Actually, one thing here you have to note that we have not considered the spin of this beta particle. If its spin will be considered, then since the beta particle has two spin states, then the number of quantum states will be just twice of this much. You have to multiply this by the factor 2, because the beta particle will have two spin state. One is plus half state and another will be minus half state, that is up spin and down spin. Then the number of quantum states will be 8 pi v by h cube into p beta square dp beta. Okay. But I have not considered it because I have told you in the case of assumption that in this theory the spin of the beta particle has been neglected. So the number of quantum states corresponding to the momentum p beta and p beta plus dp beta for beta particle is equal to dn beta, and that is equal to 4 pi v by h cube p beta square dp beta. And similarly, if you are talking about neutrino having momentum between p nu and p nu plus dp nu, what will be the number of quantum states? Again, neglecting the spin of neutrino, the number of quantum states will be dn nu equal to 4 pi v by h cube p nu square dp nu. Okay. Now, you know that electron and neutrino are independent from one another, and so the total number of available quantum states jointly to this system will be what? Actually, these number of quantum states are just probability. So the total number of quantum states, this will be equal to dn, and that dn is simply the product of these two, because these are probabilities. So dn is equal to dn beta into dn nu. Now let's put the values which we have defined here. So dn will be equal to 4 pi v by h cube times this much times 4 pi v by h cube times p nu square dp nu. Okay. So this is the total number of quantum states of the beta particle and the neutrino when we take the joint probability. Okay. So now if we want to define the number of states per unit energy, what will be that? For dE energy, the number of quantum state was dn. So for unit energy, this will be dn by dE. Okay. So dn by dE will be what? You have simply to divide the expression for dn by dE. So dn by dE will be this much. And only you have we have divided here by dE. You can see. Now the total available energy for this system will be what? Since in our system there are two particles, first one is the neutrino and the another is beta particle. So the total available energy for this system E is equal to E nu plus E beta. But remember, the energy shared by the neutrino and the beta particle when added, that is equal to total energy. But when the beta particle will share maximum energy, then this neutrino will share zero energy. Okay. So if you consider that the energy of the beta particle, that is electron's energy, is fixed, if you consider, then this E beta will be constant, and then when we will take dE, that will be equal to dE nu, because E beta has been treated as constant. Now from relativistic mechanics, you know what is the total energy of beta particle. Total energy of beta particle will be given by this formula. You have studied this formula in the relativistic mechanics, because in relativistic mechanics we know E square is equal to P square C square plus M naught square C4, you know. So E beta square, this will be equal to P beta square C square plus M naught square C4. And as the rest mass of neutrino is 0, so this term will vanish in case of neutrino, or in a case of any massless particle like photon. So if m naught is 0, then simply this E square will be equal to P square C square. That is, you can say that E is equal to Pc. So if we assume that the rest mass of the neutrino is 0, then energy of neutrino E nu will be simply equal to C into P nu. Okay. Now we will substitute these values in equation 6 here. See here. And then we will calculate the value of dNE by dE. Now you can see, this is just a simple calculation. dN by dE, this will be equal to what? 16 pi square V square by H6 P beta square. I have not changed P beta. P beta has been remain same. No, but we will change this P nu. P nu has been changed, and you know P nu is equal to what? You can see from here that this P nu is equal to E nu divided by C. But E nu from here you can see this will be E nu equal to E minus E beta. E minus E beta. You can see here. So at the place of that P nu, we have written E minus E beta divided by C. And since there is P nu square, so at the place of P nu square, you can see, I have mentioned it here, you can see. P nu is equal to E nu by C and E nu is equal to E minus E beta. So P nu will be E minus E beta by C, and since there is a square, so this is E minus E beta square over C square. Again, P beta have been written at each, but now you can see what will be dP nu by d nu. dP nu by d nu. See here. Here is dP nu by dE, but now we will write instead of E E nu. And what will be that? Since P nu, this is E nu by C, and so this is 1 by C dE nu by dE nu, and that will be simply equal to 1 by C. So your equation 6 now becomes like this. dN by dE, this is equal to 16 pi square V square by H cube P beta square times this much times dP beta times 1 by C. Okay. Now we will use this equation 6 and 7 in equation 4, where actually you have seen on the basis of time dependent perturbation theory, we have defined the probability rate of emission of this process, of this beta particle. So this is your equation 4, and you can see if we will substitute the values of this dN by dE here, okay, and also the value of psi beta 0 and psi nu 0, and we have seen the value of psi beta 0 and psi nu 0 both are equal to 1 over V root half. Let us see, just the page has been turned, but don't be worried, it will be just okay now. You can see it here. So see, psi beta 0 and psi nu 0, this is equal to 1 over V to the power half. So when we will substitute all these values in that equation 4, you can see what will be your result. See here, P of P dP. I have not written here P nu d and P nu. Only P has been written instead of the P beta, because now there is only one momentum term. So P beta has been replaced by simply P. Okay, and we have actually changed the energy momentum of the neutrino in terms of momentum and energy of the beta particle. So now this P of P dP measures only the probability of emission of beta particle, not of both. This is probability of emission of beta particle. Okay, and that will be what? According to equation 4, there was a factor 2 pi by h bar, you have seen, and this coupling factor G square was present, mod of M square, this matrix element was present, and at the same time there was mod of psi beta 0 and times mod of psi nu 0 and whole square. But you have seen that this is equal to 1 over root V, and this is also 1 over root V, and when you will take the square, this will be 1 over V square. So this V 1 over V square has been written at the place of this factor. Okay, and apart from that, Now we will put the value of dN by dE, and you can see this dN by dE is equal to this much. So put it here. This is 16 pi square V square C square H cube. C square, this you can see here. This is C square, this is C, so this will be C cube. And instead of this P beta, now we write only P. And this is E minus E beta whole square, and dP beta has been written dP. I have mentioned it here that P beta has been replaced by P. Okay. Now see this expression. Now here this H, you can write the Planck's constant 2 pi H bar. H is equal to 2 pi H bar. So when this H will be replaced by 2 pi H bar, and we will actually raise a power 6 on it, then after simplification your number will be in denominator 2 pi cube H bar 7. This is just a simple algebra, you can check it. Okay. And other things have been are same. Now at the place of E, you can write a square root of m naught square C4 plus C square P max square. Remember, when the energy of the neutrino will be 0, then energy of beta particle will be maximum, and that will be simply equal to total energy E. So E can be written as m naught square C4 plus C square P max square. Okay. And E beta, this will be what? This will be root over m naught square C4 plus C square P square, because now P beta is not written. At the place of P beta we are writing now P, and at the same time the remaining factor is P square dP. So this equation A actually represents the probability of emission of beta particle from the nucleus, and this was our aim to find in this lecture. You can see this probability of emission of beta particle from the nucleus is not 0, it is positive. It means according to this equation beta particle will be emitted from the nucleus, and this is the basic fact of the Fermi theory of beta decay, that the probability of this ejection process, this decay process, has been calculated on the basis of quantum mechanics using the time dependent perturbation theory, and we find that this probability is non-zero, it is positive. It means beta particle will be definitely ejected from the nucleus. If we consider that during its emission a massless particle neutrino is emitted too, then you can say that the probability of emission of beta particle is non-zero. So in this way Fermi theory explains that beta emission may take place. Okay. But the other facts of this theory we will see in the forthcoming lecture, in the second part of this Fermi theory of beta decay.